In part 9 of my lecture on parametric tests for comparing means, I'm going to give an example of the calculation using analysis of variance. Let's look at an example using some renogram analysis. The question that we're asking is, are all our staff producing consistent results for renogram analysis? And the data we have are kidney relative function from the same renogram analysed by 5 different operators, and each operator repeated the analysis 6 times. So we want to compare 5 groups, those are our 5 operators, with 6 repeats in each group. So we're going to use a one-way analysis of variance because we've just got one set of groups, with replication because we've got repeats in each group. Here is the example data showing 5 different operators calculating the relative function of the left kidney of this one renogram, and they've each done it 6 times, so in each column we've got 6 different measurements. The order of the rows in each column doesn't matter because they're just 6 repeats of the same thing, and the ordering is quite arbitrary. But the ordering of the columns does matter because these are 5 distinct operators and each operator could be different. You can see that the results are all round about 54% for the relative function, but there's a bit of variation between them, and what we want to know is this significant? This is all hypothetical data for illustration only, but it shows the sort of thing that one could do with real data. If we put that into Excel, Excel will do an analysis of variance using its data analysis tool, and here is the output that it produces. It shows that for our 5 operators we have 6 repeats in each group. It gives the sum of the measurements, the average and the variance. It analyses the source of variation as either between groups, that is for different operators, or within groups, that is the repeats within the group, which is the residual. It gives a sum of squares and a degrees of freedom for each source, and the mean square, which is the sum of the squares divided by the degree of freedom, and an F value, which is the mean square of 10.58 divided by the within groups mean square of 1.83. So the F value of 5.77 is bigger than the critical value of 2.76. So we have a significant result with a p-value of 0.002. So we interpret that result by saying that the F value, as we saw, calculated from the between groups mean square divided by the within groups mean square, that is 10.58 divided by 1.83, is 5.77, and it tells us that for a significance level alpha of 0.05, the critical value is 2.76. So our result is significant because we have exceeded the critical value of 2.76, and it says the significance is a p equals 0.002. So we conclude that there is a significant difference between groups, that is between operators. So not all operators are giving the same value. In fact, if you go back and look at the data, you'll see that operator 5 has a mean higher than the others, so maybe we suspect that operator 5 is the odd one out. So the obvious thing to do is to repeat the analysis but leaving out operator 5. So here we've got the analysis of variance just for operators 1, 2, 3 and 4. We find now that the F value is 1.13 and the critical value is 3.09. So we haven't exceeded the critical value now. We have a p-value of 0.358, which is not significant. So the new F of 1.13 hasn't exceeded our critical value of 3.09, and we have a non-significant result. That means that there is no significant difference between these operators. After we've left out operator 4, the other operators are all consistent. So that's one useful conclusion. But even more useful is the reproducibility, because the error mean square, or the residual mean square, from the analysis of variance was 2.09. Remembering that that's like a variance, we can take the square root to get the standard deviation. The square root of 2.09 is 1.4. That tells us that the standard error, or the precision, of this measurement of relative function is 1.4%. So that's a useful measure of the reproducibility of relative function measurement on this patient by our different operators. It gives us some idea about how reproducible, how reliable the measurement of relative function is. That's if it's processed by different operators, but it was only one patient. So we can ask another question: how reproducible are the results for relative function calculated from the renogram over a variety of patients? And to do that, we take the kidney relative function from 6 different renograms, 6 different patients, but again analysed by 5 different operators. This time, for simplicity, I've not included any repeats. So we have 5 groups, that's our 5 operators, and 6 patients. These are fixed effects because they're matched in the same way as our patients were matched when we did a paired t-test. These patients are matched because some will have good function, some will have poor function, but that's going to be consistent all the way across the operators because every operator will process every patient. So we're going to use a two-way analysis of variance without replication. Here's the data. Again, it's hypothetical data only, but it shows the sort of thing that might happen in reality. The 5 operators are shown across the columns and 6 patients down the rows. We can see that the average value of relative function for each patient is quite different. Quite naturally, the patients are all different. Some with good relative function of 55%, and patient 2 has a very poor relative function in the left kidney of only 8%. So if we do an analysis of variance, this is what Excel comes up with. The mean square for the rows is very large, and the mean square for the columns is 2.55, and the error or residual mean square is 3.71. So the row effect, which is the patients, has an F value 418, which is very large compared with the critical value of 2.7. It far exceeds it, which means it is highly significant. The p-value of 1.6 e minus 19 means 1.6 times 10 to the minus 19, an incredibly small value, telling us that there is certainly a difference between all the patients. But we don't need an analysis of variance to tell us that. We expected that. We know there is difference between the patients. That's to be expected. Of more interest is the column effect, which is our operators. And we see there that the F value is 0.69 compared with a critical value of 2.87. So it hasn't reached the critical value. There is not a significant effect between columns. So we conclude that there is no significant difference between operators. Of most use is the reproducibility. The error mean square, as we said, is a measure of the precision or the reproducibility of these measurements. And the mean square was 3.7, so if to calculate the standard error, we take the square root of that. The square root of 3.71 is 1.9. So that is the standard error of the variability of these measurements. In other words, the precision of the measurement. But remember that we usually talk about 95% confidence limits, which are plus or minus 2 times the standard error. So that is plus or minus 3.8% in the measurement of relative function. So we can say that plus or minus 3.8% is a measure of the reproducibility of relative function measurements on a variety of patients by different operators. While this value is only a hypothetical one, it does show the sort of thing that might happen in practice. So we're saying that for a renogram to have a significant difference in relative function, it would have to change by more than 3.8% to be outside our 95% confidence limits. Anything within a change of plus or minus 3.8% is not going to be significant on the basis of this sort of statistical analysis. So analysis of variance is a very handy way of analysing this sort of data. So that's the end of part 9 of this lecture on comparing means.